So now we are going to look at the moment of inertia of some standard bodies. So let us start by looking at the case of a hollow cylinder. So here we are given with a hollow cylinder of mass m, length L and radius r. So let us start our analysis by taking the case of a small strip of mass dm as shown in this figure. We can clearly see that each and every point in the strip is located at the radial distance from the center. That is, each and every point in the strip is located at a distance r from the axis of rotation. So the moment of inertia of this elemental strip can be written as dm times r square. So the net moment of inertia of this hollow cylinder can be written as integral of di, that is integral of dm times r square. Now as r square is constant, which is same for all the strips, we can write it as this. So the net moment of inertia of this particular strip can be written as r square times m. So we obtain that the moment of inertia, let me write it again, of a hollow cylinder is m r square. Now let us analyze the case of a solid cylinder. So in the analysis of a solid cylinder, we are going to exploit the result that we just derived for the case of a hollow cylinder. So how are we going to do our analysis? So in this case, we are going to take elemental hollow cylinders. So at a distance x of thickness dx, we are going to consider an elemental hollow cylinder. So this is from the top. At a distance x, we are taking a small element of thickness dx. So what is the moment of inertia of this elemental hollow cylinder? Let us write that down. It should be dm. If the mass of this hollow cylinder is dm, it should be dm times the radius of the hollow cylinder, that is dm times x square. So what is dm? What is the relation between dm and x? So let's try to figure that out. So in this case, as mass is distributed throughout the volume of the cylinder, we can write dm as m divided by pi r square L times the volume of this elemental strip. So how do we calculate the volume of this elemental strip? We need to find out first the curved surface area of this elemental strip, which is 2 pi xl times the thickness of this elemental strip. So it is 2 pi xl times dx. So let us simplify this equation first. So what do we get? LL gets cancelled out. So we are left out with 2mx dx by r square. So now let us calculate the net moment of inertia of this solid cylinder, which should be integral of di, which should be integral of 2m x cube dx by r square. So we can further simplify this equation as I equals to 2m by r square. This is the constant term, integral of x cube dx. Now we are going to take solid cylinder starting from radius 0, and the maximum distance where we are going to take solid cylinder is at a radial distance r. So it would be 2m by r square times x to the power 4 by 4, limits from 0 to r. So finally we get the result as I as 2m by r square times r to the power 4 by 4, which is nothing but m r square by 2. Now this was a pretty long analysis. Now let us try to analyze these two particular cases, that is the case of a hollow cylinder and a solid cylinder, in a more sophisticated and smart manner. So let's do that. So first let's try to think about the case of this hollow cylinder. So in this hollow cylinder, let us consider three elemental masses indicated by red color. Let us consider the small elemental point masses as 1, 2 and 3. We can clearly see that all the three masses are located at the radial distance r from the axis of rotation. So the moment of inertia of each of these masses di would be nothing but, if the elemental mass of each of the point mass is dm, each of them would be dm r square. If for point 1 it would be dm r square, for element 2 it would be dm times r square, even for the elemental point mass 3 it would be dm times r square. So rather than considering these 3 points as separate elements, we can consider all these points as a single element. So what we can do is, along this particular line which is parallel to this axis, along this entire line, we can consider all the points lying in this particular line as a single element. So if we do that, and if we consider all the points lying in a particular line parallel to the axis of rotation as a single element, we can just shrink the dimension which is parallel to the axis of rotation. So if we do that, we can see that our hollow cylinder just reduces to a ring. And what is the moment of inertia of a ring about its central axis, which is perpendicular to the ring? It is nothing but mr square. This is same as that of the case we derived for the hollow cylinder. So what we have done in this case, we have just shrink the dimension which is parallel to the axis of rotation, and by doing that we have simply reduced the hollow cylinder to a ring. Now let us do the similar analysis for the solid cylinder. Again, for this particular case, we can see that at different radial locations we can always shrink the points which is lying along a line which is parallel to the axis of rotation. So we can shrink all the points lying in this along this line, we can shrink all the points lying along this line. So effectively we can shrink the entire dimension which is parallel to the axis of rotation. That is, we can shrink this entire solid cylinder like this. If we just shrink the solid cylinder along the dimension which is parallel to the axis of rotation, we can see that it reduces to that of a disk. What is the moment of inertia of a disk? It is mr square by 2. What is the result we obtained for the case of a solid cylinder? It is nothing but mr square by 2. So we can always, for calculating moment of inertia, we can always shrink the dimension which is parallel to the axis of rotation. So for calculating moment of inertia about this axis which we have considered here, there is effectively no difference between a hollow cylinder and a ring, and there is no difference between the solid cylinder and a disk. So we can say that for calculating moment of inertia of a particular rigid body, we can always shrink the dimension of the rigid body which is parallel to the axis of rotation. We can also state this particular statement in a different manner. As we can completely shrink the dimension which is parallel to the axis of rotation, we can say that the moment of inertia of a rigid body is always independent of the dimension of the body which is parallel to the axis of rotation. So if we are given with a solid cylinder, we can see that its moment of inertia is independent of the height of the solid cylinder. For the case of a hollow cylinder, its moment of inertia is independent of the height of the hollow cylinder. So this particular simple yet crucial point can help you all in solving lots of objective questions in a much easier manner.